The ground is not supposed to move like this. There is a signal box alongside the track here, a solid brick structure, mortar between courses, built to last. It has been here since 1904. It was built to be permanent, and when the locomotive passes at speed, the walls shake, not violently, not enough that a man standing inside would reach for the door frame, but enough that the tea in his mug draws a circle on the surface, enough that the plaster above the window has been recording the event for years. A hairline crack, then two, then a tracery of fine lines running from the corner toward the sill. The locomotive is a large two-cylinder express engine, two outside cylinders, two counterweighted driving axles doing the work that the reciprocating machinery above them cannot fully account for. It weighs 87 tons in working order. Its static axle loading is within the permitted limit of 20 long tons. By every measure that matters to a civil engineer reviewing a bridge schedule, it is acceptable. What the civil engineer's schedule does not record, what no schedule recorded until 1928, is what this machine is actually doing to the ground it passes over. That is what this channel is for. Before we continue, if this kind of railway history matters to you, consider subscribing to the channel. Every video here is built around the locomotives and railway systems that the standard histories overlooked, the machines that outperformed their celebrated counterparts, the engineering decisions that were ahead of their time, and the railway lines that shaped nations without receiving the recognition they deserved. If that is the kind of documentary worth watching to you, the subscribe button is how you tell us, and we want to hear from you. Did you work on the railways as a driver, a fireman, a fitter, a signalman, a track engineer? Did a parent or grandparent spend their career on a railway that is no longer operating, on a locomotive class that is no longer preserved, or in a workshop that is no longer standing? Leave it in the comments. The people who actually operated these machines know things that do not appear in any published railway history. We want to hear from them. Now, back to the locomotive. The engineers who designed two-cylinder express locomotives in Britain during the first 2 decades of the 20th century were not careless men. They understood steam pressure, valve timing, and adhesive weight. They had produced machines capable of hauling 600 tons over long gradients at sustained speed. Their locomotives were, by any measure of practical performance, capable. What they did not fully understand, what no one fully understood until 1923, was the force their machines were putting into the ground on every revolution of the driving wheels. That force had a name. It was called hammer blow. Every steam locomotive has reciprocating masses. The pistons, the connecting rods, the crossheads, that move back and forth along the cylinder axis with every stroke. They cannot be perfectly balanced. The rotation of the driving wheels can be balanced precisely. Counterweights cast into the wheel centers can account for the centrifugal forces of the crank pins and coupling rods with engineering exactness. But the pistons move in a straight line, and a straight line force cannot be cancelled by a rotating weight without introducing a new force at right angles to it. The compromise that locomotive engineers reached was overbalance. Additional weight was added to the wheel, beyond what was needed to balance the rotating masses, to cancel part of the reciprocating force horizontally. It worked. The locomotive ran more smoothly fore and aft, but that additional rotating weight in the vertical plane now pushed downward on the rail on one part of the revolution and lifted upward on the next. It alternated, it repeated, with every turn of the driving wheel. At 20 miles per hour, the additional downward force was noticeable, but manageable. At 50 miles per hour, it had grown because these forces increase with the square of the wheel's rotational speed. At 70, they were large. At 100 miles per hour, the Bridge Stress Committee would find that the additional vertical force generated by a large two-cylinder express locomotive could equal its entire static axle load, 20 tons pressing down on the rail, then 20 tons of effective lift, then 20 tons pressing down again, 40 times per second, into the track, into the sleepers, into the ballast, into the ground, and through the ground, into whatever was standing near it. In March 1923, the British government established the Bridge Stress Committee. The formal terms of reference were narrow: to investigate stresses in railway bridges, especially as regards the effects of moving loads. It was a civil engineering problem stated in civil engineering language. The committee consisted primarily of railway civil engineers, physicists from the Department of Scientific and Industrial Research, and a single mechanical engineer, Sir Henry Fowler of the London Midland and Scottish Railway, added later, almost as an afterthought. What they found, over 5 years of measurement, was not narrow at all. They instrumented bridges. They ran locomotives across them at measured speeds and recorded the deflections. They developed instruments capable of capturing the dynamic stress at the moment of passage. And they found that the established practice of restricting locomotives by static axle load was missing the most important number entirely. A light two-cylinder locomotive, they reported, could impose greater dynamic loads on a bridge than a heavier multi-cylinder machine, not because it weighed more, because of what it was doing with its wheels at speed. The hammer blow from a large two-cylinder express engine at its critical operating speed was adding forces equivalent to its full static axle load to every downward stroke. The rail was receiving not 20 tons per axle, but, at peak, the equivalent of 40. Then it received nothing, as the wheel effectively tried to lift off the rail. Then 40 tons again. At certain speeds, the frequency of hammer blow coincided with the natural frequency of the bridge structure. The bridge resonated. The forces amplified. The ground beneath the bridge's foundation abutments absorbed forces that the designers, calculating only for static loads, had never anticipated. The report, published in 1928, was 215 pages. The engineering community, reading it, understood at once what needed to change. The Bridge Stress Committee's 1928 report recommended that hammer blow be limited to 25% of the static axle load at operational speed. That recommendation immediately reshaped British locomotive design. Civil engineers had been rejecting new locomotive proposals for years, not because the machines were too heavy in any straightforward sense, but because their static axle loads appeared to push against the rated capacity of underlying bridges. What the committee's work revealed was that this approach had been measuring the wrong thing. A large four-cylinder express locomotive, with its reciprocating masses divided across twice as many cylinders, generated far lower hammer blow than an equivalent two-cylinder machine. Its dynamic augment, the additional vertical force, was a fraction of what the two-cylinder design imposed. The implications were immediate. The axle load limit for multi-cylinder locomotives was raised from 20 to 22 long tons. Bridge renewal programs that had been constraining locomotive design for a decade were reconsidered, and designers who had argued for larger, more powerful express engines found that the engineering barrier was not static weight, it was cylinder arrangement. The Great Western Railway's King Class 460, introduced in 1927 with a four-cylinder layout and an axle loading of 22.5 tons, was made possible in part by the committee's findings. It was the most powerful express passenger locomotive in Britain at its introduction, and it owed its existence to an understanding of dynamic forces that had simply not existed 5 years before. But the original machines, the large two-cylinder express engines of the LNWR and its contemporaries, working the same gradients with their full dynamic augment, were running on Britain's main lines throughout this period. The signalmen in their brick boxes, the residents in the houses alongside the track, the line-side goods sheds, and station buildings with their Victorian masonry. They had all been absorbing it for years. None of them had been told what the ground beneath them was actually doing when the locomotive passed. The large two-cylinder express locomotives of Britain's pre-grouping era were not withdrawn because they failed. They were withdrawn because something better had been made possible, and the reason it was possible was a 5-year investigation into forces that engineers had known existed but had never properly measured. The signal box alongside the track was eventually demolished. The brick goods sheds were cleared. The Victorian station buildings that stood closest to the running lines were, in most cases, rebuilt or replaced long after the steam era ended. The evidence in their walls, the hairline tracery of cracks above windows, the mortar lines opening slowly along the corners, was not recorded. It was simply repaired, or it was removed. The locomotives themselves went to the scrapyard. No member of those great two-cylinder classes survives in Britain. The machines that generated the most severe hammer blow documented in British railway engineering history exist now only in the operational records, in the test data of the Bridge Stress Committee, and in the memory of the men who drove them. They were extraordinary machines, and what they were doing to the ground beneath them was something that the standard engineering practice of their era had no mechanism to measure. The Bridge Stress Committee measured it. The engineering record is clear. It is not generally in the history books. If you watch to the end of this, subscribe to the channel. There are more locomotives, more railway systems, and more engineering achievements still to document. And if you have a connection to what you just watched, a family member who drove a two-cylinder express on the LNWR or LOMS, who worked in the crew workshops, who signed off bridge inspections on the West Coast Main Line in the 1920s or 1930s, tell us in the comments. What did they drive? Which railway, which depot, which line? The people who operated these machines are not in the standard histories, but the engineering record depends on what they remember. We want to hear from them.